Hi everyone. This is the second part of the lecture on special chapters of high mathematics titled Multiperson Decision Theory. In the first part of this lecture, we've reached the point where we considered a solution of a matrix game in so-called pure strategies. And we've considered this example where the payoff matrix contained a so-called saddle point. Now, we suppose that there is no saddle point in the payoff matrix. So then there is a price difference between the ceiling price and bottom price. Now we can find a solution in so-called mixture of pure strategies or mixed strategies. Again, we go back to the payoff matrix, and instead of letting every player sticking to a single strategy at a time, we allow every player to play a combination or mixture of different strategies. So we introduce the new parameters. For example, player A, we introduce these parameters: shares or probabilities with which the player A uses or applies his strategy A1. P sub 2, the share of strategy A2. P sub 3, the share or probability of strategy A3. So, player B has the same options. He can randomize between using different strategies. For example, he applies his strategy B1 with a probability or share of Q sub 1. Strategy B2 with share Q sub 2. And Q sub 3 is the share or probability of strategy B sub 3 as played by the player B. Now, the mixed strategy will be called a game profile. And basically we need to find these shares. So this profile of the game, which is the solution of this particular game for player A, or from the standpoint of player A, is this S sub A, which contains the shares of corresponding strategies as used by player A. The same goes for player B. Again, the profile of the game as seen from the standpoint of player B, set of strategies with corresponding shares as employed by player B, and we need to set a condition. These shares must sum up to unit. So when we sum them up, share P sub 1 plus share P sub 2 plus equals 1. So this equation represents this situation. The same goes for shares of the strategies employed by the second player. We add them up and they equal to unit. So that's the second. Otherwise these shares doesn't make any sense. So that's a condition we need to put upon these shares of strategies played by player A and player B. There's a theorem stating that every zero-sum matrix game has a solution, either in pure strategies or mixed strategies, such that maximin of all payoffs times a double sum of payoffs summation across the matrix times the shares of strategies used by player A and used by player B actually equal the minimax summation of the same payoffs, but from the standpoint of the second player times shares of the strategies employed by player A and player B, which is equal to the price of the game, In previous case, this price of the game was reached only when the payoff matrix had a saddle point. Now, using the combinations of different strategies, we can reach the solution when minimax, maximin approach and minimax approach again can be reached at the price of the game meeting point. This sum is the average win for one player, player A, supposedly. At the same time, it represents the average loss for the second player, because we're dealing with a zero-sum game here. And this average win or loss comes at the condition given that they both players use their optimal mixed strategies, their profiles, their optimal game profiles, S sub A, S sub B. Now this is formal things. We don't have to understand this much, but we'll consider this using some examples. Now we'll let the players use their mixed strategies. These profiles look like this, where V is the meeting point where minimax and maximin strategies approaches actually come together, which is the price of the game. We need to introduce some more terms here. If a share of particular pure strategy is greater than 0, it means that this particular pure strategy is actually used or employed. So this share of the corresponding strategy played by player A or player B is greater than 0, such strategy is called the active or significant one. So introducing these active strategies or significant strategies allows us to simplify the process of finding solution to matrix game in mixed strategies. There's another theorem about active strategies. It basically states that if one player pursues one of his optimal strategies and the other player sticks to his active strategy or one of his active strategies, then the double summation representing the price of the game can be replaced by the single sum, where we sum the payoffs only not across entire matrix, but across the columns of the matrix or rows of the matrix, or columns of the matrix, given that other player sticks to his active strategy. So this is the payoff for player B. And player B can reach this price of the game, given that player A sticks to his active strategies. The same goes for the other player. The price of the game equal to V can be achieved by player A, given that player B sticks to his active strategy. And as a rational player, player B and player A should always stick to their active strategies, because in this case they can guarantee their maximum or maximum win for one player, or minimum loss for the other player. So as rational players, players can stick to their active strategies. Such simplification consists in replacing the double summation by single summation, single sum. Allows us to seek the shares of strategies for one and the other player separately. We can find these shares, P's and Q's, separately. Now let's apply the latter theorem for the 2x2 matrix game. Now let's suppose that player A pursues the matrix strategy S sub A, consisting of two shares, P sub 1 with an asterisk and P sub 2 with an asterisk. Player B sticks to an active pure strategy B1. Then the average win by player A will be found as this single sum. We sum the payoffs of the payoff matrix across the row of the matrix. So we multiply these individual payoffs by shares used or employed by player A. Let's go back for a second to a payoff matrix. So we multiply these payoffs, these individual payoffs, by these shares and sum them up. Times this P sub 1 times P sub 2 times P sub 3 and we get price of the game. So this simplification gives us the set of two equations, because we need to sum the payoffs up for the second row too, because the same goes for this pure strategy B sub 2 as played by the player B. Now this brings us to the system of two equations, or actually three equations, to find three parameters. So we need to find share P sub 1, share P sub 2, and the strategy price of the game. And the third equation is this one. The shares, the sum of two shares equals to 1. So basically we have three equations. First, second, and third equation to find three parameters. Now we use the general algebra to find these shares. So a solution for the game can be found by using standard algebra. In general case, or we can we write down this system of equations and now we can solve it. The solution, actually you can pause the video and check the solution. Find the solution yourself. Just solve this system of equation and check it up. The solution to the system has the form: individual payoffs, combinations of individual payoffs. In the same manner, the shares of the second player can also be found, the Q's. Q sub 1, Q sub 2. Again, we have three equations for finding three parameters. Now if we employ these formulas for the payoff matrix from example 1 we considered before, where the businessman try to hide at one of the hiding points, hiding places from the creditor. Now this game can be solved in mixed strategies. So instead of using or sticking to individual or pure single strategies, we introduce the shares or probabilities for the businessman to hide at one of these points. So actually he can randomize his whereabouts, either place 1 or place 2. The shares or probability of a businessman hiding at point 1 is P sub 1, and the probability of businessman hiding at point 2 is P sub 2. In the same manner, the creditor also cannot play better than randomize his seeking between these two places, because he can't find, or he cannot be looking for the businessman at the 2 points at the same time. So he has to randomize. Again, we introduce the probability or share for the creditor. Q sub 1 is the probability of the creditor looking for the businessman at point 1, and Q sub 2 is the probability for the creditor to look for the businessman at point 2. Now we can solve this using these formulas. So we just substitute individual payoffs into these equations and we get the solution. And it turns out that the shares of individual strategies are equal to 0.5, and the price of the game reduces to $7,500. So basically, what does this mean? It means that if this game is played more than once, then and the creditor businessman is randomizing his whereabouts with a probability of 0.5, and creditor randomizes his strategies with probability of 0.5, so he can just flip the coin and then assign heads or tails to place 1 and place 2 and randomize, just pick a place to find for the businessman by flipping a coin. Then the price of the game reduces to $7,500 instead of $1,500. Instead of, that's half. That's only half. $750. This zero shouldn't be here. Sorry, it's 75. $750. So, on the average, the businessman loses only half of his money, and creditor gains only half of this of his debt. So this is how it works. In general case, the solution to the matrix game in mixed strategies can be reduced to 2 linear programs. And the linear programs can be solved using the Excel spreadsheet standard tool, which we're already familiar with. So the first linear program is to maximize the price of the game. So one player is to maximize his price of the game, subject to constraints. The constraints are this: individual payoffs times the shares of strategies should be greater or equal than this price of the game. So summation goes across every row of the matrix of the payoff matrix. Again, we have additional condition that all shares sum up to unit, and all the shares non-negativity constrained. All the shares are positive, greater or equal than 0. From the standpoint of the second player tries to minimize, to bring his price of the game to the minimum, because the price of the game represents his losses, subject to constraints. Again, but instead of summing up these individual payoffs across the rows, we sum them up across the columns of the payoff matrix. Again, these individual sums of payoffs times the shares of the strategies played by player B should be less or equal than price of the game. And every equality or every inequality represents a single column of the payoff matrix. Again, we have to set the condition that all the shares of strategies sum up to unit and non-negativity constrained. So let's go back to this previous example, which we have found a solution to using the pure strategies approach. But let's consider it like this. Businessman has 3 kinds of goods. So these 3 kinds of goods can be denoted as different strategies. Different strategies. A sub 1, strategies. Which are to be sold on the market, where he will have a competitor selling the same kinds of goods, B sub 1, B2, B1, B2, B3. So the businessman has to play against a competitor. Businessman A doesn't know which kind of goods will be sold by the competitor mostly. And the businessman B doesn't know which kinds of goods will appear on the market additionally to his kinds of goods. However, the businessman A has the payoff matrix available that indicates expected profit given that the competitor goods will also be on the market. So this payoff matrix represents the expected profits given the combinations of goods sold by different suppliers, different businessman and his competitor. So if both businessman and his competitor sell this combination of products A1 and B1, there will be no gain, no profit for businessman and no loss for the competitor, and so forth, and so forth. These are the shares we disregard this for the moment. So we check the bottom and ceiling prices of the game. We try to find a solution in pure strategies. So if the businessman pursues his maximum strategy selling A1, he guarantees himself average profit of not less than 0.4 bucks per unit. If the competitor employs minimax strategy selling B1, his guaranteed loss will be not greater than 0.4. 0.4 per unit. Now we try to find or represent this game in in mixed strategies. We just employ those previous formulas formally, and we set up two linear programs. From the standpoint of businessmen, we try to maximize the price of the game, subject to constraints. The constraints come from the payoff matrix, which is repeated here. So we introduce this shares P1, P2, P3, and set up the constraints. So we multiply and stick to the active strategies. So 0.4 times P2, 0.9 times P3, and this should be less or equal than price of the game. The second column, the second row of the matrix will bring us to the second constraint. And the third column of the matrix will give us the third constraint. Additional condition that the shares should sum up to unit, and the second linear program from the standpoint of the competitor. We introduce the shares for the competitor Q sub 1, Q sub 2, and Q sub 3, and sum up these payoffs times the shares across the columns of the payoff matrix. The solution will appear like this, and we'll consider how to solve this particular game in mixed strategies using the Excel spreadsheet software in the next video. Here I'm just the price of the game. The price of the game can be increased from 0.4 to 0.48, given that the player A or businessman uses the shares of his strategies P sub 2 with a probability of 0.53 and share P sub 3 with a probability of 0.47. And the player B or competitor employs his active strategies Q sub 1 with probability of 0.6 and Q sub 2 with probability of 0.4. So as rational players, the businessman and his competitor should employ this combination of strategies P sub 1, P sub 2, Q sub 1, Q sub 2. Oh, sorry, P sub 2, P sub 3, and Q sub 1, Q sub 2. This is it for this video. Until next time, thanks for watching.